I want to do an example with LU decomposition, where I'll show you how to get your L, U, and P matrices, and then once you have those, how to solve your system of equations for your solution. I'm going to do this with a system of 3 equations and 3 unknowns, so I have x1 plus 2x2 plus 3x3 equals 2, I have x1 plus x3 equals 3, and x1 plus x2 minus x3 is equal to 1. So the first step here is we need to figure out our L, U, and P matrices. So we're going to decompose our A matrix so that L times U will equal P times A. And to do this, we're going to use some of our Gaussian elimination steps, but also kind of keep track of what's going on as we do this. So we're going to start by writing our coefficient matrix A, so just our coefficients from our equations. And we don't need our right-hand side, just the coefficient matrix. So 1, 2, 3, 1, 0, 1, 1, 1, negative 1. And we're going to start by doing Gaussian elimination, and there's 2 things that we need to do while we do this. First, we need to keep track with our row reduction elements. So the fraction that we use, this fraction, when we do our row reduction, we need to keep track of that. And we also need to keep track of our row order. So to keep track of the row order, I just like to write 1, 2, 3, and pay attention to any row interchanges that I do as I go through the Gaussian elimination steps. And then when we're keeping track of our row reduction factors, I'll show you how I do that as we get there. So the first step is to identify our pivot element. So it's going to be row 1, column 1 here. There's a 1 there. We check if we need to do row interchange. So the 1s are all the same magnitude, so we don't need to do a row interchange here. And we'll do our row reduction. So we'll get zeros in the first 2 columns by using our Gaussian elimination equation. So here are R2 new, here will equal our R2 old, minus, and now we do the value in the same column as our pivot element with the row we're doing reduction on. So 1 divided by our pivot element, which was 1, times our pivot row 1, and our row 3 new equals our row 3 old, minus, here now we still have a 1, so it'll be 1 divided by 1 again here, times row 1. So this gives us our next matrix of 1, 2, 3. We didn't do anything to row 1, so it stays the same. And row 2 now I have 0, negative 2, negative 2, and 0, negative 1, negative 4. And we haven't done any row interchanges, so our row order remains the same at 1, 2, 3. So 1, 2, 3. And I also said we're going to keep track of these row reduction factors. And the most common way to do this, and the way that I like to do it, is we know that doing row reduction got us zeros in that same column as our pivot element. So instead of writing the zeros here, we will write our row reduction factors. And typically we include these in parentheses to remind us that it's not actually that value. There are row reduction factors, and I'm even going to do them in a different color here because I have access to a different color. So these are actually zeros, but I'm going to put that 1 over 1, so 1 as my row reduction factor into this matrix. And then we're going to continue doing Gaussian elimination, but here we're just trying to get our upper triangular matrix, so we only need to get to zeros below our pivot elements. So we won't worry about going up, we'll only worry about going down. So our next pivot element, row 2, and it looks like we have a 1 here, but that's actually a 0, so the first column with non-zero is column 2, so that negative 2 is our pivot element. And then we only need to do the rows below that. So now I'm going to do R3 new is equal to R3 old, minus, and then this is where I have to do that fraction. So I have negative 1 divided by the pivot element, negative 2, so that'll be positive 1/2 times row 2. If we're doing true Gaussian elimination, we'd also do row 1, but for LU decomposition, we only need to do the lower things below this. So now my matrix, I didn't do row interchange again, so I still have the same row order. My top row I didn't change at all, so I have 1, 2, 3. And then this was a 0, but we're keeping track of our row reduction factors. So I'm going to keep my 1 in parentheses there and below. So it would have been 0, but 1, negative 2, negative 2. And then my last row, I have 0, 0, and negative let's actually figure that out. Yep, negative 3. And I would have a 0 in the second element, but I'm going to cover it up with my row reduction factor, which was negative 1 over negative 2, or 1/2. And this is all the Gaussian elimination that we need to do. We're done with Gaussian elimination. So now we just need to use this to get our L, U, and P matrices. So let's talk about how to do this. The first one, the easy one, is going to be the U matrix. So this is, in fact, our U matrix. We're done. We figured out our U matrix. So U, we'll put our zeros back in, and this will be our U matrix. So 1, 2, 3, 0, negative 2, negative 2, 0, 0, negative 3 is our U matrix. To get our L matrix, we put 1s on the primary diagonal. We put in our row reduction form, so row reduction factors. Those values we have in parentheses here, those become our lower triangular matrix. So 1, and then 1 and 1/2. And we put zeros in the upper part of our triangle. So it's a lower triangular matrix, so we have 0 in that upper triangle. And then our P matrix is an identity matrix in which we perform any row interchanges that we did. And here we did no row interchanges, so this is going to just be an identity matrix. But if we had done row interchange, if we'd swapped row 3 and row 2, for example, then we'd do the same row interchange in our P matrix. So then we'd have still sort of an identity matrix, but what rows correspond with which rows in our identity matrix rows could be switched. So now we've identified our L, U, and P matrices. So now we can start to use the decomposed A matrix to solve our system of equations. So after we've gotten our L, U, and P matrices, the first step in solving for our solution is to do L times a B hat vector. So this is a thing that we kind of make up for LU decomposition that makes the math really easy. Will equal our permutation matrix P times our right-hand side vector. So that's from our original system of equations, so 2, 3, 1 in this case. And typically we do the right-hand side multiplication here first, and since this is just an identity matrix, times 2, 3, 1, when we do that math, we should just get our 2, 3, 1 back out. And now we're going to use this to solve for this B hat vector. And we use forward substitution to solve here. So we don't need to do anything crazy or fancy. The beauty of the lower triangular matrix is that we can solve these one element at a time without having to solve a system. So the first row here says that 1 times B hat 1 is equal to 2. So B hat 1 equals 2 from that first row. And now the second row says B hat 1 plus B hat 2 is equal to 3. And we can plug in our 2 for B hat 1, so we'd have 2 plus B hat 2 is equal to 3. So that should give us that B hat 2 is equal to number 1, the 1. And then our last row, B hat 1 plus 1/2 B hat 2 plus B hat 3 is equal to 1. And if we plug in 2 for B hat 1 and 1 for B hat 2, then we can very quickly solve for B hat 3, and I got negative 3/2. So this gives us B hat 3 is negative 3/2. So even though it looks like an ugly matrix to solve, because of all these zeros in the upper part of the matrix, we can just use forward substitution to just solve for them one at a time without much trouble at all. And now that we have our B hat vector, I'm going to erase my U, but it's okay, I have it written down. We go to the next step, which is U times our solution vector should equal our B hat. So from my decomposition, I have a U matrix that is 1, 2, 3, 0, negative 2, negative 2, 0, 0, negative 3, times my solution vector, so x1, x2, x3, will equal my B hat vector, and that's what I just solved for. So that'll be 2, 1, negative 3/2. So 2, 1, and now we can solve this system of equations using what we call backward substitution. So we're going to start from the bottom row and move up, and again we should always only be solving for one variable at a time. So the bottom row here says negative 3 times x3 equals negative 3 halves. And from this, we can divide by negative 3 and see that x3 should equal 1 half. And then the second row here says negative 2x2 minus 2x3 is equal to 1. Plugging in 1 half for x3 and then solving for x2, we should get that x2 is equal to negative 1. So again, it looks like a system of 3 equations and 3 unknowns, but we can very easily solve them one at a time. And now we're on our top row, x1 plus 2x2 plus 3x3 is equal to 2. And you might notice actually that we've done nothing to this top row. That is our first equation that we were given at the beginning. And the whole point of this method is to do as few computations as possible in a computer. Computationally, this is the fastest method, especially with multiple right-hand sides. And so plugging in here now, our x3 is 1 half, our x2 is negative 1. We should get that our x3 is, or excuse me, my x1 is 5 halves. So if I wanted to write my solution vector here, write it out. We have to remember we did x1 last, so that's actually the first element. So it's going to be 5 halves, negative 1, 1 half. And that's how we solve a system of equations using LU decomposition. So we started by decomposing our coefficient matrix into our upper triangular matrix that we got from Gaussian elimination. Our lower triangular matrix, that these were just the factors that we used in Gaussian elimination, those row reduction factors with the ones on the diagonals. And a P matrix, which is an identity matrix with any row interchanges in that process that we kept track of. And then once we solve those, we take our L times this made up B hat vector is equal to our right hand side vector from our original equation. And we use forward substitution, so solving B hat 1, B hat 2, B hat 3 to solve for our B hat vector. And then we say U times our solution vector equals that B hat vector. And now we get to use backward substitution, so starting x3, then x2, then x1, we can solve for our solution vector.